Hello everyone, today we are going to be talking about commercial space transportation and space tourism. So a brief overview of what we'll be exploring in this presentation is we'll start with a quick introduction to what commercial space travel is and why it's become such a hot topic. Then we'll dive into the history, looking at how we've shifted from government-led space programs to private companies leading the way. We'll break down the types of commercial space flights like suborbital, orbital, and future deep space missions. We'll also take a look at the challenges facing the industry like safety, cost, and regulations. We'll learn about the propulsion systems that make these missions possible. And to end, we'll look at the future of space travel and commercial space travel and what it could end up being. So to get started, what is commercial space transportation? Well, it refers to the use of privately operated spacecraft to carry people or cargo into space for a profit. Unlike past space missions run by governments, this is led by companies like SpaceX and Blue Origin. Also, what is space tourism? This is the recreational side of space travel, where private individuals pay to experience spaceflight, even if it's just for a few minutes. It's a growing market with flights now being offered by companies like Virgin Galactic or Space Perspective, which you see the capsule in this image is what they're trying to do in the future. Okay, so let's take a quick look at how we got here. For decades, going to space was something only trained astronauts could do. Missions were run exclusively by national space agencies like NASA and Russia. But in the early 2000s, private companies like SpaceX and Blue Origin began developing reusable rockets. This was the game changer everyone needed. Then in 2001, a major milestone happened when Dennis Tito became the world's first space tourist when he flew to the International Space Station. That moment provided that space travel could extend beyond government missions. Now we're in a new era where commercial space companies are leading efforts to make space tourism more accessible for regular people. And now, we're no longer just dreaming about space, we're actually planning to visit it. So now let's break down the three main types of commercial space flights. First, we have suborbital flights. These are short trips that go to the edge of space, around 50 to 100 kilometers up, where passengers experience just a few minutes of weightlessness before returning to Earth. This is what companies like Virgin Galactic and Blue Origin currently offer. Next, we have orbital flights. And this is where spacecraft actually enter orbit around the Earth, typically at altitudes around 400 kilometers, like the International Space Station and where our other satellites usually orbit. These missions can last anywhere from a few hours to several days, where SpaceX is currently leading the way with their Crew Dragon capsule. Finally, we look toward the future with lunar and deep space missions. These involve planned trips around the moon or even to Mars someday. They're still in development phases, but companies like SpaceX and Blue Origin are actively working on making this possible. Each of these flight types opens up different possibilities and different challenges for commercial space travel. So here we have a diagram that helps us visualize the difference between suborbital and orbital space flights. The orange arc represents a suborbital flight. It goes up past the Kármán line, about 100 kilometers, which is considered the edge of space. It reaches space but doesn't have the speed to stay in orbit. Passengers get just a few minutes of that weightlessness before descending back to Earth. Now when we look at the blue arc, this is a full orbital flight. These missions travel much higher, around 400 kilometers altitude, and reach the velocity needed to actually orbit the Earth. This is the difference between just visiting the edge of space versus actually circling the planet. Companies like Blue Origin focus on suborbital trips, while SpaceX is leading in orbital missions.
So taking civilians to space isn't just a technical feat, it's a challenge of safety, affordability, and sustainability. So first, with safety, rockets are complex machines. They operate under extreme conditions. Malfunctions, high G-forces, and limited emergency protocols pose significant risks, especially for passengers without astronaut training. Second would be cost. So a single ticket can range from $250,000 to tens of millions. And right now, space tourism is only accessible to the ultra-wealthy. Reducing costs and making it affordable is a major hurdle for this industry to grow. And finally, the environmental impact. So rocket launches emit carbon and black carbon into the upper atmosphere, while reusable systems like the Falcon 9 help reduce waste. We still need to study these long-term effects. These three areas, safety, affordability, and sustainability, are the key barriers that shape how commercial spaceflight evolves. Commercial spaceflight brings extreme thermal and fluid challenges that engineers have to solve to keep both passengers and hardware safe. So starting off with re-entry heating, as the vehicle descends back through the atmosphere, it experiences temperatures of over 1650 degrees Celsius. So to protect the spacecraft, we use thermal protection systems like ablative carbon phenolic materials or reinforced carbon-carbon composites, such as those used on the SpaceX Crew Dragon. So for vacuum heat transfer, in space there's no air, so convection doesn't happen. That means all the heat transfer has to occur through radiation. And to manage this, the spacecraft uses radiators with high emissivity surfaces and sometimes combine them with passive or active cooling loops. Moving on to engine cooling. So inside rocket engines like the Merlin 1D, combustion chamber temperatures can reach over 3,000 Kelvin. And so to prevent structural failure, many engines use regenerative cooling, where cryogenic fuel flows through channels along the nozzle walls before it's injected and burned. And speaking of cryogenics, both liquid oxygen at negative 183 degrees Celsius and liquid hydrogen at negative 253 degrees Celsius need highly insulated tanks. These use multiple vacuum layers and vapor-cooled shields to reduce boil-off during flight and long pre-launch holds. And finally, there's cabin thermal control. For crewed flights, systems have to manage both heat and humidity. That includes liquid-cooled garments, CO2 scrubbing, and phase change materials. Crew Dragon, for example, uses a human-rated environmental control system to keep passengers safe and comfortable for hours in orbit. Together, these challenges make thermal fluid design one of the most demanding parts of commercial spaceflight. So there are three main propulsion systems used in commercial spaceflight today. We have chemical, hybrid, and reusable liquid engines. Starting off with chemical propulsion, SpaceX uses liquid oxygen and refined petroleum-1, also known as RP-1, a highly refined form of kerosene in its Merlin 1D engines, producing around 300 seconds of specific impulse. It's reliable and relatively easy to handle. Blue Origin, on the other hand, uses liquid hydrogen with liquid oxygen, which gives better efficiency, about 450 seconds of ISP, meaning better fuel efficiency, but it is harder to manage since liquid hydrogen must be stored at negative 253 degrees Celsius, making the system more complex and harder to handle from both a thermal and structural standpoint. Hybrid propulsion is another approach, seen in Virgin Galactic's Spaceship Two. It uses a solid fuel called HTPB and a liquid oxidizer, nitrous oxide. This system is simpler and more restartable. It makes it more ideal for short duration suborbital flights where operational safety and reliability are critical. Finally, reusable engines are redefining how we approach launch costs. SpaceX's Merlin 1D, for example, operates using a gas generator cycle, producing around 845 kilonewtons of thrust per engine. These engines are engineered for 10 or more reuses and can be restarted mid-flight, which is essential for recovery maneuvers and cost-effective operations. Rocket nozzles are one of the most critical components for generating thrust in space vehicles. They use a convergent divergent or de Laval shape to accelerate gases to supersonic speeds. Inside the throat of the nozzle, the flow chokes at Mach 1, meaning it reaches the speed of sound and then expands outward, increasing velocity and reducing pressure. To be efficient, the nozzle's exit pressure needs to match the surrounding ambient pressure. If it's too high or too low, you get flow separation or shock losses that reduce thrust. Now, a key metric that tells us how well this process works is specific impulse. It measures how much thrust you get per unit mass of propellant. A higher ISP means your engine is more efficient. For example, liquid hydrogen and liquid oxygen combinations have a higher ISP than RP-1 based systems, but they're also harder to store. So in short, nozzle design directly affects propulsion performance, and ISP is what we use to measure that performance across different fuel types and configurations.
Next, let's look at some of the vehicles that are currently in the space tourism industry. The SpaceX Falcon 9 and Crew Dragon has orbital flight and is powered by 9 Merlin engines. The vehicle holds 7 occupants, and it's the first human-rated private orbital spacecraft. It has boosters that land vertically and is one of the first. The Blue Origin New Shepard has suborbital flight and is powered by a BE-3 engine. It holds 6 occupants and is fully autonomous in the launch and landing. It has a soft parachute recovery and very high specific impulse. The Virgin Galactic Spaceship Two has suborbital flight and a hybrid motor. It has 6 seats also, but unlike the other two of the seats are meant for captains to man the flight. Some of the key features are that it has unique feathered re-entry system for aerodynamic stability and launches from a carrier aircraft, unlike the other 2 that launch from the ground. Taking a closer look at the SpaceX and Falcon 9 company and vehicle, it was founded by Elon Musk. The first flight was June 4th, 2010, but the first human space flight was May 2020. It's the first rocket to be reusable and lightweight, and it's used for a variety of missions, such as resupplying the International Space Station, launching Starlink, or human spaceflight. It's a 2-stage vehicle, the first stage powered by the 9 Merlin engines arranged in an octaweb structure, and it's fully reusable and autonomous. It contains landing legs and a cold gas thruster to bring it safely back to Earth. It's meant to complete the flight, even if one of the engines fail. The second stage is a Merlin vacuum. There are about 4 versions of this vehicle, with the latest being the most upgraded and the safest. SpaceX boasts a launch success rate of about 99%. It has 455 complete flight missions, 410 total landings, and 382 total reflights. Next is the Blue Origin and the New Shepard. The first human spaceflight was achieved July 20th, 2021, and it contained 4 crew members, none of which were astronauts, and the founder, Jeff Bezos. The goal of the company is to pave the way for space tourism and eventually life in space. It is a single-stage vehicle with the BE-3 aforementioned engine. The vehicle briefly reaches the Kármán line, which is considered to be the edge of space. The flight is approximately 11 minutes long, but the crew only experiences microgravity or weightlessness for about 4 of those minutes. The flight and the landing are all vertical, and the crew capsule is landed using soft parachutes. The vehicle is meant to be flown fully autonomously without anybody manning the ship, and is meant to be comfortable, smooth, and built for great viewing. The crew capsule and booster are all reusable. Last, let's talk about the Virgin Galactic and Spaceship Two. The first fully crewed flight was on July 2021, but the first commercial flight was June 2023. There was a major crash in 2014 that led to major redesigns and some changes for further safety and further comfort. Redesigns improved the user-friendliness and the training failures of the crew members that were not trained astronauts. Because of this, the vehicle is not autopiloted. It has 2 captains that man the flight. It launches at 50,000 feet in the air from a mothership called White Knight 2, reaches a height unlike the other 2 that launch from the ground. But the crew is also able to experience microgravity or weightlessness for about 4 minutes. The rocket engine is hybrid, and the tickets are worth about $500,000 per seat. For space tourism, some of the design considerations and safety features include passenger safety, cost, and comfort. In passenger safety, we have to consider user-friendliness, sufficient life support, backup systems, and emergency protocols, escape systems, minimal required training, automation, communication with launch control, reliability and high launch success rate, protection from solar radiation and extreme heat, and software integrity. Because the vehicles are meant for tourism, it's supposed to accommodate to different types of users that are considered is cost, which means that rockets should be reusable for many flights, and the purchase of tickets should be somewhat accessible to comfort. For example, the Blue Origin has large windows for optimal viewing. The capsule should also be spacious, and the landing should be smooth and accurate. Because the tourists are not trained for very long, it should have lower G-forces. The flight and the landing should not only be accurate and easy, but it should also make it more endurable and more comfortable, and thus more accessible for people that are not trained astronauts to go to space.